Welcome to the next lecture on mobile radio propagation. The brief outline of today's talk is as follows. We will start with the summary of what we have learnt so far, followed by a brief description about the Rayleigh fading and the Rayleigh distribution. Then we will look at the Rician distribution, followed by two real life useful parameters, the level crossing rate and the average duration of fade. Both these things will somehow translate to your quality of service. So, a brief recap. We have learnt so far that there can be two kinds of channels, the frequency flat as well as frequency selective channel. They depend somewhat on the coherence bandwidth. Then we have looked at various channel models for the frequency flat as well as frequency selective fading, followed by slow and fast fading, which has something to do with coherence time. In this slide, we have put on one single sheet the notion of flat / slow fading, flat fast fading, frequency selective flat fast fading and frequency selective slow fading. On the two axes, we have the transmitted period Ts. Here is a vertical line which marks the coherence time Tc. On the y axis, again we have the symbol Ts, and this line marks the RMS delay spread. So, if your Ts is larger than the root mean square delay spread, you are in the domain of flat fading. And again, at the same time, if your Ts, the symbol time, is greater than the coherence time, then you enter the domain of flat fast fading. Okay. Similarly, you have the other options. You can look at the same slide from a different perspective, that is from the bandwidth, baseband signal bandwidth. On the x axis, I have the symbol bandwidth B of s, so also on the y axis. However, the vertical line approximately relates to the BD, the maximum Doppler shift. On the y axis, we have the BC, the coherence bandwidth. Now, please remember, coherence bandwidth was a function only of the multipath components in the channel and had nothing to do with the signal. So, I can shift and vary my BS independent of the BC. Doppler depends upon how fast the vehicle is moving with respect to the base station, or how fast the transmitter and receiver are moving with respect to each other, and has nothing to do with BS, right. So, in that case, again I can move independently BS, the symbol bandwidth, independent of BD, and again I work either in the domain of flat slow fading or frequency selective fast fading or any other combination. Now, what we want to do today is slightly different. We would like to look at the actual fading profile, look at what kinds of distribution actually come up when you have a line of sight or you do not have a line of sight, and then how does this affect your level crossing rate or average duration of fade. Because if you are sitting in a fade for too long, you will tend to lose not only the signal but also the synchronization. Ultimately, it will lead to dropping your call. So, what do we mean by fading distributions? The statistical characterization of the variation of the envelope of the received signal over time is captured by the fading distribution. Please note, we are only talking about the envelope, right? Some notion of the signal power being received here. Of course, you have some distributions regarding the phase, but usually the phase is uniformly distributed over 0 to 2 pi. What is interesting is the variation of the envelope of the received signal. We will find that this envelope undergoes deep fades once in a while, depending upon what kind of a fading distribution you have. The two most common distributions are the Rayleigh fading and the Rayleigh fading. You have generalizations of Rayleigh fading in terms of a Nakagami fading distribution, but we will talk about it later. These are by far the most common fading distributions. We will in the subsequent slides today talk about the Rayleigh fading and the Rayleigh fading distributions. When does Rayleigh fading occur? If all the multipath components have approximately the same amplitude. That is, when the mobile station is far away from the base station and also does not have a clear line of sight, because that will be definitely the strongest component. So, in the absence of a line of sight and when all the multipath components have roughly the same amplitude, then the envelope of the received signal is Rayleigh distributed. Please note, we are only commenting on the envelope, although what you receive will have an amplitude and phase. Clearly, we do not have any dominant signal component such as the line of sight or any one reflector which is a strong reflector. It is assumed all the reflectors are equally strong or equally weak, depending upon you are looking at it pessimistically or optimistically. Let us now look at how Rayleigh fading actually appears when you carry out an experiment. Suppose you have an envelope detector sitting in a car and you have a way to store the data. So, you have a receiver with an envelope detector and a means to store the data, and you drive away from the base station. On the x axis, we have plotted the elapsed time in milliseconds for a car which is traveling at about 120 kilometers per hour. So, clearly, using the fact that the speed of the vehicle is 120 kilometers per hour and this is the elapsed time, you can find out how much distance you have traveled away from the transmitter or the base station. On the y axis is plotted the signal level in dB about the RMS. Now, please note that we start from 10 dB, but it goes down way up to minus 40 dB. And in certain cases, you have these deep nulls, also called the fades. They are called fades because if you listen to a radio, for example, and you are sitting in a fade, the sound will diminish to a point that you can hardly hear it. So, it is a faded signal that you receive. Please note that all the edges are pretty much rounded because we are talking in terms of a log plot. It is a dB scale. Otherwise, you will get a fairly jagged variation as you move in a car with a receiver at 120 kilometers per hour. Now, what is of concern are two things. How many times per second do we get into the fade? For that, we must define what is an acceptable signal strength, below which we say that the signal is not usable. So, we need a threshold, and then we need to come up with a parameter which tells me number of crossings, level crossings per second. Later today, we will try to define a level crossing rate. Now, as I mentioned before, the y axis in this graph plots the envelope. Given this distribution, which is found out to be Rayleigh, if you plot the histogram of the values here, you will come up with a distribution which is resembling the Rayleigh distribution. If you have this distribution, then statistically, if you draw a horizontal line here and define a threshold, then you can statistically calculate the number of crossings per second. That will be the level crossing rate. The other thing of importance is what is the average duration of fade. For that, I need to know again a threshold. So, let us draw a line here. Then how much time do we stay below that line? That will give me the average duration of fade clearly if I give you the PDF, probability density function of the Rayleigh distribution, then I can statistically calculate the average duration of fade. We will find that out also. We will also look at some examples. Question?
Sir, if the mobile station is on the edge of the circle that is surrounded by the BS, okay, base station is the center. So when it's moving, so the equidistance is there. So Rayleigh feeding will be there, or is some variations over there?
Okay, let me repeat the question. The question being asked is, suppose we approximate the cell by a circle with the base station at the center of the circle and the mobile station is moving along the circumference. That is, it is equidistant from the base station. So we are not really translating across this axis which is moving away from the base station. We are just moving in a circle. Right? Clearly, the path loss is not changing because the distance d is not changing. Question being asked is, will we still undergo fading? The answer is yes. Suppose we are really at the circumference of the base station, the probability of having a line of sight is very low, right? So you will have components which are coming by reflections, and the moment you have multipath and then they add up either destructively or constructively, we get a fading. So fading will be there, and in this case most likely Rayleigh fading. So clearly if you move around the circle of the base station, you will see similar effects. What this means is that if you draw an average line somewhere, the average signal strength will gradually go down. The car has not moved very much in 250 milliseconds actually at this speed. But if you have not moved at all, that is, you are translating across a circle's circumference, you have not moved in terms of the distance d, but still you will have this kind of a variation. You will get fading. Okay. Now let us look at the other realistic scenario, that you are indeed closer to the base station, or you have a single dominant reflector. In either of the cases, not all of the components, the reflected components, are equal in strength. So even then when they add up, they do not form a Rayleigh distribution, but something called as the Riccian distribution. So when there is a single dominant stationary, which is non-fading signal component present, such as the LOS, which is usually possible when the mobile station and base station are relatively close to each other, the fading envelope is not Rayleigh but Riccian. Now the Riccian distribution slowly degenerates to the Rayleigh distribution when the dominant component fades away. Clearly, in the Rayleigh fading scenario, if we add one dominant component, we get the Riccian distribution. In fact, if we somehow have a measure to see how much signal strength is in the direct component as opposed to the reflected components from other reflectors, that ratio will tell us how far away is the Riccian distribution from the Rayleigh distribution. Fine. Let us go back to the Rayleigh distribution and see what is it mathematically. The PDF, or the probability density function of the Rayleigh distribution, is given by the following. PR, PDF, is r over sigma squared e raised to power r squared over 2 sigma squared. There is a minus sign here. This is valid for r between 0 and infinity, okay, and it is 0 for negative values of the r. Please remember, this is the amplitude, the envelope. Okay, so there is no question of this becoming negative. This is obtained by taking the square root of the squares of two Gaussian random variables. Now, this sigma is of importance. As in Gaussian distribution, sigma is a measure of the spread of the distribution. Here, sigma is the root mean square value of the received voltage signal before the envelope detection. Sigma square clearly is the time average power of the received signal before the envelope detection. So, the mean, the median of this distribution all will depend on this sigma. Fine. The probability that the envelope of the received signal does not exceed a specified value of R is given by the cumulative distribution function CDF. Now, this is important because you can have a PDF, but at the end of the day you are interested in finding out how often does it fade. What is the probability that the envelope received at the receiver is above a certain threshold level? How often is it above the receiver sensitivity? Okay. So, it is important to find out the probability that R is less than R, and then to find out the other case we will find out 1 minus P of R. This is nothing but from 0 to R is the threshold level, PR dr. If you integrate it, you get this expression 1 minus e raised to power minus R squared over 2 sigma squared. Also, you can calculate the R mean, the R medium and the R RMS, root mean square. So, these are certain properties of the Rayleigh PDF. Let us quickly look at it. The mean value is given by sigma under root pi over 2. It's just 1.25 times sigma. It's fairly close to this sigma value. The median on the other hand is close to 1.177 sigma, okay, and the root mean square RMS value is given by root 2 sigma. Fine. So, please note that the mean and the RMS value are fairly close to each other, 1.25 sigma and 1.414. Some properties of the Rayleigh distribution. It is by far one of the most common distribution used for mobile radio propagation. How does it look graphically? Okay. On the y axis we have plotted the PDF, right, and this is the distribution, the Rayleigh distribution. The mean nearly equal to the standard deviation sigma. The tail is much larger than the normal distribution, than the Gaussian distribution. Okay. The spread is much larger. And we can say that you are in a deep fade when P is greater than 3 sigma. So, there is a mean value here given by under root pi by 2 sigma, and this is the standard deviation sigma, okay, fairly close. It is a very slowly falling tail. Clearly, if you change the sigma, right, then the PDF will become more constrained to the initial values. So, it will become, the spread will reduce. Let us look at 3 typical values. Sigma is equal to 1, 2 and 3, and you can see that the spread increases as you increase the sigma. This is a typical Rayleigh PDF. So, what you have to see is when you take into consideration the Rayleigh PDF, you have to find out what is the sigma for your case, and then based on that sigma you have to take your calculations, and later on the average durations of fade and the level crossing rates both will depend upon the actual value of sigma. So, if the number of scatterers increases, okay, fine, then your sigma will tend to increase. Also, there will be an effect on how fast you are moving. So, you have to do the measurement, right, plot a histogram, determine your sigma and do the further calculations. Now, let us spend some time talking about the Rician fading. Clearly, we need to have one dominant line of sight. When there is a dominant stationary non-fading signal component, then the fading envelope is Rician. The Rician distribution, as seen before, degenerates to the Rayleigh when the dominant component fades away. Okay. What will happen when there is not one but two dominant components, or just three dominant components from different directions? Well, it is not Rician anymore, it is not Rayleigh anymore. You will have to look at certain other kinds of distributions like the Nakagami fading distribution to capture these effects. But right now, let us limit ourselves to a single dominant signal component. Mathematically, the Rician distribution is given by the following. P of r is again for r greater than or equal to 0, r over sigma squared e raised to power minus r squared plus a squared divided by 2 sigma squared I naught ar over sigma squared, and 0 for the negative values of r. Clearly, it is the envelope of the signal. So, I should not have any distribution for r less than 0. Here in this equation, a denotes the peak amplitude of the dominant signal. It had to come somewhere. If I put a is equal to 0, I should go back to my Rayleigh distribution. Fine. I naught denotes the 0th order Bessel function of the first kind. I0, 0 is 1. If you put a is equal to 0 here, then you get r over sigma squared e raised to power minus r squared over 2 sigma squared, which is exactly the Rayleigh distribution. Fine. So, clearly, you have filtered in the effect of the dominant signal into the probability density function. The Rician distribution is often described in terms of a parameter k, where k is a squared divided by 2 sigma squared. Please remember, a represents the most dominant component and sigma is the strength of all the other components. So, it tells us the energy or the ratio of the energy in the dominant component with respect to all other components. If we have a tending to 0, we must go back to the Rayleigh distribution. On the other hand, if a is much larger than sigma squared, that is, all the other reflections are kind of negligible with respect to the signal which is in the dominant component, then you should somehow tend to the Gaussian distribution, right. So, there are two extremes of the Rician distribution. Sometimes k is represented in terms of dB. So, k in dB is nothing but 10 log a squared over 2 sigma squared dB. Please note, we are talking about the power here, a squared, right. A is the signal strength, a squared represents the power component. Therefore, we are using the 10, not 20 log here. Now, for k much greater than 1, when the signal in the dominant component is much stronger than the other components, then the Rician distribution tends to the Gaussian distribution about the mean. Fine. So, then your analysis of the fading channel will just become the analysis of the additive wide Gaussian noise channel, you have no fading. You cannot have fading if you have just a dominant line of sight. If there is only one component which is strong and all the multipath components are negligible, there is no fading. Fading comes from multipath components. On the other hand, if k tends to 0, which means there is no line of sight, what dominates is the multipath components, and then you must have fading. How does it look? Well, here we have plotted different Rayleigh PDFs for various values of k. Please note the sigma is 1 for all of them. What we have done is started with no clear line of sight component to a weak dominant signal to a stronger dominant signal, and so on and so forth. So, as we move along this axis, I am getting a stronger and stronger and stronger dominant line of sight component. Clearly, when k is equal to 0, we have the Rayleigh distribution, and as you move away, you get away from the Rayleigh and quickly move to a distribution which somehow starts looking like a Gaussian distribution. However, this distribution is centered around the mean. So, what is this? This is the PDF of the envelope of the received signal. Clearly, if you have to do a calculation for the level crossing rate or the average duration of fade for a Rician distribution, you have to now use the PDF for the Rician distribution as opposed to the Rayleigh distribution. Please observe that for k much greater than 1, the Rician distribution is really tending towards the Gaussian distribution about the mean. Fine. This is the second most popular distribution that we use when we have the line of sight. Now, let us get into some of the practical aspects. What do we do with this distribution? What kind of information do we gather or infer from this distribution? So, first of all, if I have to comment something about how many times do I dip below a certain threshold and what is the average duration I stay below a threshold, I must come up with either the level crossing rate or the average duration of fade scenarios. So, how do I carry out this experiment? First, I will take a lot of measurements. I will get into a moving vehicle with a receiver and an envelope detector, and I will find out how my signal strength is varying. I will take a lot of measurements. I will plot the histogram of the envelope. If I am in a Rayleigh fading channel, I will get something which resembles the Rayleigh distribution. Based on that, I will find out the sigma. Then I have the complete specification of my PDF. Once I have that, then I will find out how many times I go below a threshold or how many times I stay below the threshold. Let us look at it mathematically. The level crossing rate, or LCR, is defined as the expected rate at which the Rayleigh fading envelope normalized to the local root mean square sigma level crosses a specified threshold level in the positive going direction. So, it is a very clear cut definition. Please note couple of things. Here we are talking about the Rayleigh fading envelope. However, you can have LCR for other distributions as well. At the end of the day, it only deals with how many times do the signal level crosses a specified threshold in a positive going direction. Okay. So, you got into a fade and then you are going up. After some time you got into the fade and you are going up. Each time you cross that threshold, you count 1. And at the end of a certain duration in time, you find out how many times you did that, cross that threshold line, divided by the total number of amount of time you took the measurement for, and you get the level crossing rate in terms of numbers per second. The number of level crossings per second is given by this formula, which is easily obtained from the Rayleigh fading distribution. It is NR given by under root 2 pi Fm rho e raised to power minus rho squared. Now, please note there are two interesting parameters here. One is the rho, the other one is Fm, or the maximum Doppler spread. What is rho? Rho is what we define in terms of a ratio. R is that special threshold value, and R RMS is a characteristic of the Rayleigh distribution. If you go back and check, R RMS depends on the sigma. Fine. So, it will be root 2 times the sigma. So, your rho is simply given by the threshold you defined divided by the R RMS. Fm, on the other hand, deals with how fast you are traveling and at what angle is the ray from the base station coming towards you. Okay. So, Fm can be found out by that. Once you have these two numbers, then you have the Rayleigh, for the Rayleigh, the level crossing rate in terms of crossings per second. How strong is the effect of rho? How sensitive is the number of crossings per second to your threshold? These are the things we will look at today with some examples. Clearly, if you fix up a high R, then the rho will increase, but it is e raised to power minus rho squared, so number of crossings will go down. It is intuitive. Okay. In a distribution, if you increase the level of your threshold, then the number of times you cross it per second will decrease. On the other hand, if you have a very low threshold, you will tend to cross it many number of times per second, but it is e raised to power minus rho squared. Let us look at an example. Let us describe a scenario, maybe a typical GSM scenario. Let us say we have a really Rayleigh fading environment. So, we are in an urban environment, fairly far away from the base station, clearly no line of sight. The carrier frequency, let us say, is 900 megahertz. It is important to observe that the carrier frequency will play a role in your level crossing rate. How much, how sensitive it is to carrier frequency, we will look at some other examples also. But for this example, let us say it is 900 megahertz, because this will translate to your wavelength, which will translate to your FM, the Doppler shift, which will translate to your level crossing rate. Let us say that the maximum vehicular speed is 50 kilometers per hour. Clearly, it is a congested urban scenario. The rho is 1. Who has specified this rho? We ourselves as design engineers can specify a rho. It will depend really on the quality of service you wish to provide and of course your receiver sensitivity. But for the sake of illustration only, let us say rho is equal to 1, that is your threshold. R is equal to the RMS, and R over R RMS is nothing but 1. What do we have to find? find out the number of crossings per second going in the positive direction. So, first we have to calculate the wavelength at which we are operating. So, it is the speed of electromagnetic waves divided by the frequency is equal to about 33 centimeters. The maximum Doppler shift is V cos theta divided by lambda, but let us assume that theta is equal to 0. So, it is V over lambda. 50,000 meters per second divided by 3600 seconds per hour. So, V over lambda gives me 41.67 hertz. This is the maximum Doppler shift. Now, at this stage we can quickly put these values in this equation, under root 2 pi fm rho e raised to the minus rho squared, and we get 38.42 crossings per second. Is this good or bad? What do we do with this value? It tells me that for this particular situation, okay, and here please note that the sigma has not come into the picture because I have specified rho is equal to 1. Otherwise, your answer should and will depend on the sigma. Okay. But assuming rho is equal to 1, then you have close to 40 crossings per second. 40 times you are dipping below the fade and going up again. Okay. Most likely you have to do something about it. Not a very healthy scenario. But then you are calculating it for 50 kilometers per hour. Now, let us look at the next important parameter, which is the average fade duration, sometimes also referred to as the average duration of fade in the literature. This is the average period of time for which the received signal is below a specified level R. This R can be specified by us and has to be a function of the receiver sensitivity or the minimum quality of service we wish to give. For Rayleigh fading distribution, this average fade duration is given by, first of all, when you calculate it, it is tau average is 1 over n r, probability that r is less than a specified threshold r, and if you carry out the simple calculations using the Rayleigh distribution, you get tau bar is equal to E rho squared minus 1 in the denominator rho Fm, Fm being the maximum Doppler spread, under root 2 pi. Rho is defined as before, R, the threshold fixed by us, divided by the R RMS, comes from the sigma of the PDF of the Rayleigh distribution. So, let us look at it again. Clearly, it is a very strong function of rho, e raised per rho squared. So, if rho is greater than 1, this 1 is usually neglected. So, in the denominator, in the numerator you have e raised per rho squared. The denominator has also a rho and Fm. See, if you travel much faster, then your Fm should increase. So, the value of the denominator increases, your average duration of fade will go down. You will get out of the fade very fast, right? But this has nothing to do with how quickly you get back into the fade. So, there are two things. If you move fast, this Fm goes up, right? But you must also remember that just staying below a threshold depends on how fast you are traveling, but very soon you might get back into the fade. That must come from this NR. That is the significance of NR. You couldn't have calculated the average duration of fade without the notion of the level crossing rate. Fine, they are interrelated. Let us look at the average fade duration with an example. Let us describe a scenario. Let it be similar to what we did in the previous example, a GSM scenario. It is a fading channel. The carrier frequency again is 900 megahertz. It will help us calculate the lambda. We stick to our maximum vehicular speed of 50 kilometers per hour. Again, fix rho is equal to the root mean square value. The task this time is to find out the average duration of fade. The lambda or the wavelength is calculated to be 0.33 meters or 33 centimeters. The maximum Doppler shift again comes out to be 41.67 hertz, because I have fixed my speed at which I am traveling at 50 kilometers per hour, and the lambda is also fixed. If you now plug in to the equation for the average duration of fade, you get a value of 16.5 milliseconds. Again, the question before us is it good or bad? What do we do with this number? So one thing is clear. If we are suppose designing an interleaver to overcome the fade duration, then this value will tell us how deep my interleaver should be. If we are trying to do block coding of some sorts for channel coding to overcome the effects of errors, then we must make the errors look like they are random errors. However, the moment you have fades, you wipe out series of bits. So what happens is you have burst errors. Fading channels normally will lead to burst errors. Now, if you have a data rate, okay, so if you are sending 1000 bits per second, then multiply with 16.5 millisecond and you know how many bits have been erased. Clearly, you work at much higher data rates. So, you are talking about hundreds of thousands of bits that can easily get erased for this fading situation. It is a very unhappy situation to be in, unless you do something about it. The easiest way is to put in an interleaver with an appropriate depth, so that these burst errors appear as random errors and hence can be overcome by block codes. So this is the significance. Clearly, this single number owes its genesis to your sigma, which has been found out by actual measurements, right, or a modeling of the channel. Okay. So at the end of the day, the channel models, channel measurements will give you a Rayleigh distribution with a certain sigma, which will give you the average duration of fade, which will help you design an interleaver, which will help you give you or guarantee a certain bit error rate. If you do not want to do all of that, you have to change your R, the threshold, because if you change your R, the sigma changes. But to change your R, you can either pump in more power. Okay? So you can give a fade margin, pump in more power, change your R, and consequently change this value. It can be shown that increasing just the signal strength is not always the best way to overcome the effects of fading. It is a wasteful method, though a simple one. Let us look at another example. Here on the x axis, I have plotted the vehicular speed in kilometers per hour. on the y axis I have plotted the average duration of fade in milliseconds. Okay. But I have taken 3 scenarios because I would like to see the effect of the threshold. So, I have rho is equal to 1, which tells me that my threshold value r is equal to the root mean square RMS value. Here it is 0.1. So, r is much less than the RMS value. In fact, it is a tenth, and here it is a 20th, 0.05. Now, on the y axis is the duration of fade in milliseconds. As you can see, let us follow the first curve. As you increase the vehicular speed, right, the average duration of fade decreases. It is an interesting phenomenon. Even though as you increase the vehicular speed, the level crossing rate increases, on an average the duration of fade decreases. So, it is good news. A vehicle traveling at a faster rate, right, will have less burst errors. It is somewhat intuitive also. Whereas, if I sit on a red light for a long time, or if I go very slowly, I may stay in a fade for a long time. So, the average fade duration increases. So, as I go towards the left side of this axis, say at 20 kilometers per hour, my average fade duration could be 40 milliseconds. Now, see what happens when you change rho. Okay. Now, the moment I lower my threshold, there is a drastic fall, because it is e raised to power rho squared. It is a very strong impact. So, even at 20 kilometers per hour, your average duration of fade has gone down to close to about 2.5 milliseconds, and it is still further for rho is equal to 0.05. Fine. So, yes, there is a way to overcome the fading by providing for fade margins, and in some communication systems you do provide for fade margins. You pump in a little bit more power. This will translate to playing with your threshold level. Okay. Also, another thing, beyond a certain speed, the decrease in the average fade duration is not significant. Also, if you note, for low values of rho, okay, the function of the vehicular speed does not show up prominently. There is not a significant impact on the speed of the vehicle on the average duration of fade for low values of rho. It is more pronounced when rho is 1 or greater. So, these will translate to your design issues. Let us look at another example. This is relevant for various frequencies of operation. Clearly, average duration of fade is important. It will kill my situation, it will kill my synchronization, it will cause burst errors, it will cause very poor bit error rates if I do not think of overcoming average fading durations. And how to overcome that will first ask me to find out what is the average duration of fade. But the average duration of fade is also a function of the frequency of operation. Just look at the two bands, the 900 megahertz band and the 1800 megahertz band. Here, let us consider the rho is equal to 1 scenario. So, the threshold R is equal to the RMS value. This one we have seen before, 900 megahertz for rho is equal to 1. So, at 20 kilometers per hour, you get average durations of fade up to 40 milliseconds, and if you go up to 100 kilometers per hour, you are down to only 10 milliseconds. But see what happens if you switch to, if you have a dual band and if you just switch from 900 megahertz to 1800 megahertz, you have drastically lowered your average duration of fade. This is not very intuitive. Okay. In fact, what it will show up in your actual measurements is that your level crossing rate increases drastically, but level crossing rate is in the denominator for tau bar. So, it has caused a decrease in your average duration of fade. Just by translating to a higher frequency of operation or a smaller wavelength, you have improved your situation. Your burst lengths have decreased. Of course, everything is not so rosy. The moment you go to a higher frequency band, you hope to pump in more number of bits per second. So, even if your duration of fade has gone down, the bit rate has gone up. So, maybe the number of bursts, number of bits in burst error probably stays the same, although it does not decrease linearly. And then when you go from 1.8 gigahertz to the more familiar ISM band of 2.4 gigahertz, and then clearly 2.4 was never designed to be for very high vehicular speeds, but it can allow you low portability. Right? Here in this region, the effect is prominent. Again, the general trend remains the same. The average duration of fade has gone down, and for lower speeds the effect is pronounced, whereas if you tend to move to slightly higher speeds, you tend to flatten out. Fine. So, this is an interesting observation for rho is equal to 1. If you now make this rho equal to 0.1, you go much below. Please note, 2.4 gigahertz scenario is not so rosy as it appears, because here you have to go towards the left of this axis. 20 kilometers per hour is much higher than what is expected in the 2.4 gigahertz range for which we normally design our systems, and so the moment you go towards the left, you tend to go up. So, it will still be a problem. So, you have to understand the average fade duration and design your communication systems accordingly so as to overcome the effects of fading. Fine. So, let us now summarize what we have learnt today. We started off with Rayleigh fading and Rician fading. We looked at not only the fading, but the distribution. We looked at the PDFs. Then we looked at one derivative of the Rayleigh fading distribution, which is the Rayleigh level crossing rate. How many times per second do you cross a certain threshold in the positive direction? Finally, we looked at another important parameter, which is the average duration of fade. Okay. We also looked at some examples to see how the threshold value, which is a function of the rho, makes a difference in terms of the average duration of fade, and even how the wavelength of operation or the frequency of operation changes the average duration of fade. We will conclude our lecture here and will continue further in the subsequent lectures. Thank you.